very good afternoon everyone. Just confirm me whether audio video is clear. Kindly confirm audio video is clear. Kindly confirm just audio video is clear or not. Is my audio video clear to you? Just confirm it once. So a very good afternoon everyone. Myself Prateek Mishra and I welcome you all to the YouTube platform of IMS Gate Academy. We are conducting the foundation series just to help you make your basics strong so that you can fight for Gate 25 with a very strong hold and you can apply all the concepts properly. In this series, we have already discussed three very important topics. We started with the water demand, then we have discussed about the physical water quality parameters, some of the basics, how to calculate the total solids, suspended solids and dissolved solids. Then we have talked about the basics of chemistry which will be used in solving the question of chemical water quality parameter, and in the yesterday's session we started with the sedimentation analysis. I have given you some of the basics of the sedimentation analysis in which we have discussed what are the different factors which affects the sedimentation and on which property the sedimentation depends. Today we will going to continue from there itself, but before we continue, I would like to make few announcements. The first announcement is related to our Telegram group, my dear student. The link is given in the description box. You can join our Telegram group to have the lecture PDFs, YouTube session details. We also post regular quizzes so you can enjoy the daily quizzes on our Telegram group. And last but not the least, we provide you with all the job notification updates by the means of videos, and we also conduct the webinars and seminars to help you oriented and help you to make aware about new things that are coming up in the market of gate industry. Chalo. Next, we at IMS Gate Academy, we provide you with 4 different types of courses where we provide 800 hours of live teaching along with live interaction and doubt solving. We provide you with theory and exercise book containing 4000 plus practice questions well versed in level 1, level 2 and level 3. Along with that, my dear students, we provide you with an exclusive GATE question bank containing 34 years of GATE question in which we have provided the detailed solution, alternate solution, video solution along with key points and chapter overview. So if you look into the total question practice that we provide to you is like 4000 plus 4000, that is total of 8000. Along with that, we provide you with India's largest test series containing 130 plus tests, is starting from chapter test, subject test, multiple subject test and the full length mock test along with the advanced subject test. In the full length mock test, you will also get the video solution of the questions, especially for the challenging question. Last but not the least, my dear students, IMS Gate Academy is the only institute in the country to provide personal mentoring to our students. We provide you with one-to-one mentoring sessions, and these mentoring sessions helps you to orient and plan your studies properly so that you have a very efficient GATE preparation throughout your entire journey of GATE preparation. So these are some of the announcements. By these announcements, I like to continue for the yesterday's session. We have talked about the very economical process of removing suspended solids from the raw water. That economical process is known as the sedimentation. In sedimentation, we simply allow the solids to settle under their own weight. You can see I have just mentioned 2 examples. This is the construction going on for a horizontal flow type sedimentation tank, and this is the final working unit of horizontal flow type sedimentation tank. So sedimentation is one of the most economical treatment given to raw water where we remove the suspended solids. In sedimentation, the solids settle under their own weight, and while settling they have a constant velocity which is known as the settling velocity of the solids. Then we have seen the different factors which affects the settling of the solids, in which we have seen The first factor is velocity of flow or turbulence. So if velocity of flow and turbulence is more, then the settling of the solids will be less. Second is the viscosity of the fluid. If viscosity of the fluid is more, then the resistance offered by the fluid against the settling of solid will be more. Hence, the settling will be less. Third one is the size of the particles. So if you are comparing n number of particles having same specific gravity, then more the size of the particle, more will be the settling of solids. From there, we have shifted to the sedimentation analysis, how we actually design these tanks, what all things we do. So first of all, my dear students, for designing these sedimentation tank, especially the continuous flow type sedimentation tank we are talking about, for designing the continuous flow type sedimentation tank, there are certain assumptions that we take. But before designing, we need to analyze this tank, then only we can design. Yesterday, I have told you that designing the sedimentation tank means determining the value of different components of the sedimentation tank. That includes the length of the tank, height of the settling zone, then width of the tank, then velocity of flow, volume of the tank, all those things. So designing means simply finding out the value of different components of the sedimentation tank. But before designing, we need to analyze the tank. For analyzing the continuous flow type sedimentation tank, the first assumption that we took is concentration of particles of all sizes is same at all the points of the vertical section of the inlet end. Even after finishing the entire course, most of the students don't understand what this simple thing means. So I was discussing this point only yesterday and then I have stopped because this point and the further analysis again will require more than an hour. That's why I have kept another session for this particular decision. Now see this, my dear students. You have this sedimentation tank like this. You have this sedimentation tank like this. This is your sedimentation tank. Now see how the things goes. This is your sedimentation tank. This is your inlet. This is your inlet, right? And this is your outlet. I haven't drawn any wall, any boundary of the sides, just to give you the clear-cut idea what actual process is happening, right? So whatever I am saying, please understand very carefully, because nobody explains this and nobody gives you this much clarity. So this is your inlet end and this is your outlet end. Now see what is happening. Water is entering from the inlet end like this. Water is entering from the inlet end like this, right? Now when this water will enter from the inlet end, there will be some turbulence present in the water. So we need to reduce this turbulence, okay? Because if turbulence will be more, settling of the solids will be less. So when the water is entering from the inlet end, there will be some turbulence in the water. So we need to reduce this turbulence. In order to reduce this turbulence, we provide some extra length over the design length. Means for designing, if we have calculated the length of the tank as 10 meter, then we certainly increase this length to 1.15 to 1.3 by this factor. Means by 15 to 30% we increase this length. Now see this. This much space I will be providing, so that the turbulence that is coming from the inlet end can be reduced. This much space I will be providing so that the turbulence coming from the inlet end can be reduced, right? This much space, right? I am just talking about this much space. This much space or this much length is provided. This length is provided to reduce the turbulence. This much length is provided to reduce the turbulence, right? So water is entering into the tank. then this much length will be provided to reduce the turbulence. Now when this water will travel over this length, this water will be uniformly distributed over this cross-sectional area. This water which is entering from this inlet will be uniformly distributed over this cross-sectional area like this. It will be uniformly distributed over this cross-sectional area. And this cross-sectional area from where the design length is starting is termed as the cross-sectional area of the inlet. So this is your cross-sectional area of the inlet. Clearly I am mentioning this. This is the cross-sectional area of the inlet. This is your cross-sectional area of the inlet. This green line that I have drawn, this is your cross-sectional area of the inlet. This green line that I have drawn is your cross-sectional area of the inlet. This section XX is the cross-sectional area of the inlet. Now I think the things are clear to you. Water is entering from the inlet, then water is uniformly distributing over this entire depth. And when the water is uniformly distributing over this entire depth, it means that whatever is the concentration of solids, it will also be distributed over this entire depth. The concentration of solids of all the sizes will be uniformly distributed over this entire depth. That is what we mean by assumption number 1. The concentration of solids will be uniformly distributed over this entire depth, and this section XX is my section of inlet. This is my section of inlet. This section XX is my section of inlet. This is my section of inlet. This is my section of inlet. This is my section of inlet. I think now it is clear. Now it is very much clear that what analysis we will going to do. Usually, yesterday I have drawn one diagram where I have just drawn one pipe which is connected to the tank. And all the faculties, they actually explain using that diagram. So it is very hard to imagine if the water is entering from the top, how it is instantaneously getting distributed over the entire depth. But it is getting distributed over the entire depth because this much amount of length we have increased over the design length. And that is why traveling in this length, the water will be evenly distributed over this entire depth, and along with the water, concentration of solids of all the sizes will be evenly distributed over this entire depth. Okay, this is my assumption number 1. Now coming to assumption number 2. Assumption number 2 says that the particle is assumed to be removed if it reaches the bottom of the settling tank. Particle is assumed to be removed means particle will only be considered to be removed if it reaches bottom of the settling zone or settling tank. You see this. Yesterday I have drawn this diagram. This is my settling tank. One second here. So this is my settling tank, right? In this settling tank, there are 2 zones. The upper one is my settling zone and the lower one is my sludge zone. Upper one, this is my settling zone. This is my settling zone. This is my settling zone. And the lower one is my sludge zone. This is the sludge zone. Second assumption is saying is, this is the section XX from where I will going to analyze the tank, right? This is my section XX from where I am going to analyze the tank. This is my section XX from where I am going to analyze this tank, okay? If the particle reaches bottom of the settling zone like this, if the particle reaches bottom of the settling zone, then only we assume that this particle is removed. If the particle reaches the bottom of the settling zone, then only we assume that it is removed. if the particle does not reach the bottom of the settling zone, you can see this particle is not reaching the bottom of the settling zone. So we do not assume that this particle is settled. This particle is not removed. This particle is not removed. This particle is not removed, and this type of particle will not be considered for calculating the efficiency of sedimentation. Only those particles which reach the bottom of the settling zone will be considered for calculating the efficiency of sedimentation. Even if your particle is here and if it reaches the bottom of the settling zone, then this will be considered as removed. So all the particles which are reaching the bottom of the settling zone are considered to be removed. And the height of the settling zone, yesterday I have told you that this height, we take it as capital H. This height, we take it as capital H. Okay. So these two assumptions are clear to you. First one is, at the inlet section of the settling tank, the concentration of particles of all sizes are uniformly distributed. Second one, a particle is assumed to be removed only if it reaches the bottom of the settling zone. If the particle is not reaching in the bottom of the settling zone, then we do not consider this particle to be removed. Simple. Now let's see how we design this tank. First of all, these sedimentation tanks are designed for the removal of suspended solids. These sedimentation tanks are designed for the removal of suspended solids. So I'll write here, sedimentation tanks are designed for the removal of suspended solids. Are designed for the removal of suspended solids. Now you know that if this is my water sample, it will contain all the sizes of suspended solids. If this is my water sample, it will contain particle of all the sizes like this. It will contain particle of all the sizes. If this is my water sample, in this water sample, there will be all the sizes of particle that will be present. Now you see this. What is the purpose of designing? The purpose of designing is to make this particle reach the bottom of the settling tank, right? Reach the bottom of the settling zone, sorry. What is the purpose of designing? The purpose of designing is to make all the suspended solids to reach bottom of the settling zone. If a particle has to reach bottom of the settling zone, if the particle has to reach bottom of the settling zone, they have to travel by the vertical distance of h. Okay. If the particle has to reach bottom of the settling zone, they have to travel this vertical distance of h. Now you see this. These are the particles of different sizes. Say the velocity settling velocity of this particle is Vs1. For this particle it is Vs2. For this particle it will be Vs3. For this particle it will be Vs4. For this particle it will be Vs5. For this particle it will be Vs6. Okay. Since the velocity, settling velocity of all these particles are decreasing, in order to sir karna crack gate in last 2 years in my BTech, definitely you can crack. In last 2 years of BTech, for gate only 8 months is required. You have 2 years. So you have this particle of different sizes having different settling velocity, right? So different particles will going to have different settling velocity. In order to remove all these particles, they have to travel by the height of h. Sir, is there any force between the drop? No. there is a force, there's a relative force between the drop and the fluid around it, and that is known as the drag force. Even the force of buoyancy is present on the particle. So when you derive this expression of settling velocity, all those forces we consider. So three forces will be acting. One is the weight of the solid, second one is the buoyancy offered by the fluid, and third one is the drag force, which is the relative force when the particle is settling in the fluid. So three forces will be acting, and considering these three forces, we have derived this settling velocity expression. Okay. So I was telling you this, now you focus on this, right? That is the later part of discussion. When the particles have to reach the bottom of the settling zone, they have to travel by the height of capital H. It is but obvious that if the settling velocity is more, the time required by this particle to reach bottom of the settling zone will be less as compared to the time required by the particle which is of smaller size. All these particles have to travel by the vertical distance of h to reach the bottom of the settling zone, right? What about cohesive and adhesive force? That you read in fluid mechanics. Right now we are discussing environment, so you focus here. The particles of different sizes, they settle with different velocities. All these particles have to travel a distance of h in order to reach bottom of the settling zone. The particle having more settling velocity will require less time as compared to the particle which is having smaller size. So if the settling velocity is decreasing like this, means Vs1 is more than Vs2, is more than Vs3, is more than Vs4, is more than Vs5, is more than Vs6, is more than Vs6. So this is the order of the settling velocity. All these particles have to travel the same height h in order to be removed. Now for this particle to be removed, the time required by the first particle to reach height h or travel by height h is t1. Since Vs1 is more than Vs2, therefore the time required by the particle to reach or to travel by the vertical height h is T2, and obviously T2 will be more than T1 because Vs2 is less. Time required by the third particle is T3, which will be more than T2. Time required by the fourth particle is T4, which will be more than T3. Time required by the fifth particle is T5, which will be more than T4. And the time required by the sixth particle will be T6, which is more than T5. All these particles have to travel a vertical distance of h. Now the question comes, if we want to focus on the efficiency of sedimentation, right? A very good afternoon, Amit sir. If we need to increase the efficiency of sedimentation, it means our sedimentation tank should be capable enough to remove even the smallest size of the particle. But just for the sake of removing the smallest size of the particle, the time that should be available should be huge, or it comes out huge. In order to remove the smallest size of the particle, the available time for settling should be T6. And you can see here, T6 is huge. Now, how we provide this time T6? This time T6 is provided by increasing the length of the tank. Sometimes, just for the sake of removing the smallest size of the particle, just for the sake of removing the smallest size particle, the detention time comes out to be huge. Now, in order to maintain this detention time, you need to provide the length. Length of the tank, right? What is this time? This time is the time for which the water stays in the tank. Now, in order to provide this time, you need to provide the length of the tank. Sometimes in order to remove the smallest size of the particle, the times comes out to be huge, and corresponding to that, if you started providing the length, this length starts coming out in kilometers. This length starts coming out in kilometer, which is not at all feasible to provide. Now what we do? We first design the tank for the concerned size of the particle. Say this is my concerned size of the particle. In simple words, the sedimentation tank is designed for the removal of concerned size of the particle. Concerned size of the particle is that particle which is not the smallest particle, but it is that particle which is having sufficient size so that feasible detention time can be provided. Feasible detention time can be provided. So all the sedimentation tanks are designed for the removal of concerned size of the particle. Say this is my concerned size of the particle. 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 All the sedimentation tanks are designed for the removal of concerned size of the particle. Concerned size of the particle. Concerned size of the particle. All the sedimentation tanks are designed for the removal of concerned size of the particle. Now for this concerned size, first I will calculate the detention time that I have to provide. I am designing the sedimentation tank for this concerned size of the particle. Now, if I am designing the tank for this concerned size of the particle, first I should calculate the time that I should provide in this tank for water to stay so that this size of particle can be removed. So in simple words, first I have fixed which particle I need to remove, and that particle is known as the concerned size of the particle, and for the concerned size of the particle we design the sedimentation tank. Second, corresponding to the concerned size of the particle, we calculate the time required. You can see here, this is the concerned size of the particle, and this is the time required by the concerned size of the particle to settle or to reach the bottom of the settling zone. This T3 is the time required by the concerned size of the particle to reach bottom of the settling zone. Simple. So I will just summarize this. Sedimentation tanks are designed for the removal of concerned size of the particle, or any sedimentation tank is designed any sedimentation tank is designed for the removal of concerned size of the particle. Any sedimentation tank is designed for the removal of concerned size of the particle. For the removal of concerned size, say small d, of the particle. Concerned size of the particle. Now for this concerned size of the particle, small d, the settling velocity is Vs. By this settling velocity, this particle has to travel the distance, vertical distance of h. Can we say that it depends on the size of the particle? Yes, my dear, it depends on the size of the particle. That is why we have chosen this concerned size. Okay. The detention time or the length of the tank actually depends on the size of the particle. If you try to remove a smaller size of the particle, then you have to provide huge length of the tank. And sometimes that is not feasible because it comes out in kilometers sometimes, right? But for this concerned size of the particle, we get the adequate length which is actually feasible to provide, even economical to construct. Okay. So all the sedimentation tanks are designed for the removal of concerned size of the particle. This concerned size of the particle will going to have the settling velocity Vs. And by the use of this settling velocity, the concerned size of the particle has to travel the vertical distance of h. the time required by the concerned size of the particle to travel the vertical distance of h is termed as the detention time of the tank or the retention time of the tank. This is known as the detention time of the tank, detention time of the tank, also known as the retention time of the tank, also known as the retention time of the tank. So if any word is given to you, you can use it either way. Retention, why I am getting, so this is detention time or retention time or retention time. So out of all the sizes of particle, we design the sedimentation tank for the removal of concerned size of the particle. Out of all the sizes of particles that are present in the water, we design the sedimentation tank for the removal of concerned size of the particle. This concerned size of the particle will going to have one settling velocity, and by the use of this settling velocity, if this particle travels the vertical distance of h, the time required will be Td. And Td is nothing but the detention time of the sedimentation tank or the retention time of the sedimentation tank. Please focus here, we are talking about the concerned size, and with respect to the concerned size, I have just defined one parameter that is known as the detention time of the tank. Once you decide the concerned size, at that moment only you will going to calculate the detention time. Now detention time is fixed because this detention time is provided by constructing the length of the tank. Now what is this detention time? Detention time is that time for which water stays in the tank. Means if the water is entering from the inlet till the water is exiting from the outlet, that time is known as the retention time or the detention time. So detention time is that time for which water stays in the tank. Detention time, it is that time for which water stays in the sedimentation tank. Water stays in the sedimentation tank. Water stays in the sedimentation tank. So don't confuse, right? Sedimentation tank. Water stays in the sedimentation tank. Now second, how we maintain this detention time? This detention time is maintained by the length of the tank. This detention time is maintained by the length of the tank. Means if I have to make sure that the water stays in a tank for 1 hour. How can I maintain that? I can maintain that by providing sufficient length of the tank based on the velocity of flow. I will provide sufficient length of the tank so that if the water is traveling by some velocity of flow, by this velocity of flow, the water should take that much time to reach the other end of the tank. So this detention time is maintained by the length of the tank. Detention time is maintained. Detention time is maintained. Detention time is maintained by the length of the tank. Detention time is maintained by the length of the tank. Very, very simple, right? This detention time will be maintained by the length of the tank. Now you see this. So sedimentation tanks are designed for the removal of concerned size of the particle. We have discussed. Okay. Chalo, we'll start one by one. So we start the analysis of this. You see, So this is my longitudinal section of the tank. This is the longitudinal section of the tank here. And this is my inlet cross section. Okay, so this height is the height of the settling zone. This height is the height of the settling zone. You see this. This is the height of the settling zone. This is capital H. This is capital H. This is the height of the settling zone, capital H. Okay. Now you see this. Your concerned size of the particle is present at the top of this height. Your concerned size of the particle is present at the top of this height. From here onwards, the analysis is very, very important. You see this. Your particle is present at the top of this height. Okay. This particle is flowing with the horizontal velocity of Vf. It is flowing with the horizontal velocity of Vf, which is known as the velocity of flow. And simultaneously, this particle has a settling velocity of Vs. This particle has the settling velocity of Vs. Okay. This is your particle which is flowing with the horizontal velocity of Vf and have the downward velocity of Vs. That is your settling velocity. When you take the vector addition of these two velocity components, you will find out that this particle will travel along this direction, that is along the diagonal direction. By Vf, this particle will move horizontally forward. By Vs, at the same time, it will going to move horizontally down. It will going to move vertically downwards. So when you take the vector addition of these two velocity components, the path traveled by this particle comes out to be diagonal like this. Due to these two velocity components, the path traveled by this particle will be diagonal like this. It will be diagonal like this. Okay. And after time dt, after time dt, after time td, right? Sorry, after time td, this particle will reach the bottom of the settling zone here. After time td, the particle will reach the bottom of the settling zone here. After time td, this particle will reach the bottom of the settling zone here like this, right? So, in this time td, the particle has traveled the vertical distance of h, so that is equal to h upon Vs. Okay. In this time td, the particle has traveled the vertical distance of h, and at the same time td, particle has also traveled this horizontal distance, and this horizontal distance is nothing but the length of the tank. This horizontal distance is the length of the tank. This is the length of the tank. That is your design length. This is the length of the tank. This is your length of the tank. This is your length of the tank. So in this time td, the particle will travel the vertical distance of h, and at the same time td, the particle will also travel the horizontal distance of l. So this time td is also equal to l divided by Vf. Very, very important relation. Very, very important relation. Detention time is equal to h upon Vs is also equal to L upon Vf. Okay. This is the case where the concerned size of the particle is present at height capital H. This is my case number 1, where the concerned size of the particle is present at height capital H. TD time you have already provided, and this TD time is provided by constructing the sufficient length of the tank. This length of the tank will ensure that the particle or the flow or the fluid stays in the tank for time TD. Okay. So for this time TD, it is calculated as H upon Vs, and it is also calculated as L upon Vf. So this is my case number 1, when the concerned size of the particle is present at height capital H. Concerned size of the particle is present at height capital H. So now tell me whether this particle is removed or not. In the available time TD, it is reaching the bottom of the settling zone. This is my settling zone, right? Capital H height. Since this particle is reaching the bottom of the settling zone in available time TD, therefore this particle is removed from the system. So case 1, case 1, concerned size of the particle D present at height capital H, present at height capital H, right? So in the available time TD, this particle will be removed. In the available time TD, this particle will be removed. This particle will be removed. Okay. This particle will be removed. Now here only I would like to tell you few things. First one is the settling velocity of the concerned size of the particle, that is Vs. Vs is the settling velocity of the concerned size of the particle. The settling velocity of the concerned size of the particle is also known as surface overflow rate. This d is the concerned size of the particle, and we are talking about the concerned size. Settling velocity of the concerned size of the particle is known as surface overflow rate. So settling velocity of concerned size of the particle, settling velocity of concerned size of the particle, that is small d. Settling velocity of concerned size of the particle is termed as surface overflow rate. Is termed as surface overflow rate. SOR, and this is nothing but Vs. Vs is the settling velocity of the concerned size of the particle. So surface overflow rate, Vs. Surface overflow rate is nothing but the settling velocity of the concerned size of the particle. So from case 1, I would like to make two conclusions. First one is, if the concerned size of the particle is present at height capital H at the inlet section of the sedimentation tank, then that particle will be removed in the available time TD. Again, it's a huge statement, so again I'll repeat this. If the concerned size of the particle is present at height capital H at the inlet section of the sedimentation tank, then in the available time TD, it will be removed from the system. Okay, simple. Now let's see some of the derivation here only. Okay. So you see this. So this is my settling tank, right? And I'm only drawing the settling zone. There is no sludge zone here. I'm only drawing the settling zone. This is my settling zone, capital H. This is the length of the tank L. This is the length of the tank L, and this is width of the tank B. This is width of the tank B. This is height of the settling zone H, and this is length of the tank. And the water is flowing like this. Throughout the entire depth. I have told you, right? We provide that length in order to compensate for the turbulence created at the inlet end. We provide that additional length in order to compensate for the turbulence created at the inlet end. So this is how the flow is taking place. You can very well visualize the flow like this. What is the velocity of flow, anyone? The velocity of flow is Vf. This flow is taking place at a constant velocity Vf. This flow is taking place at a constant velocity Vf, like this. This flow is taking place at a constant velocity of Vf, like this. This is how the flow is taking place, right? This flow is taking place at a constant velocity of Vf. This velocity of flow is Vf. So can I write down the discharge that is flowing through this? So the discharge flowing through the cross section discharge that is flowing through the cross section Q is equal to velocity of flow multiplied by this cross sectional area, and this cross sectional area is nothing but B into this height of the settling zone, that is H. So this is equal to B into H. This is your velocity of flow, right? Now this velocity of flow can be written as, you can see here, this velocity of flow can be written as detention time divided by the length, or it can also be written as, this velocity of flow can also be written as Vs into L divided by H. This velocity of flow can also be written as Vs into L divided by H multiplied by B into H. So this H and H will going to cancel out. So Q is equal to Vs into B into L, right? And this B into L is nothing but the plan area of the sedimentation tank. This B into L is nothing but the plan area of the sedimentation tank. B into L is the plan area of sedimentation tank. This is the plan area of the sedimentation tank. B into L is the plan area of sedimentation tank. This Vs is nothing but the surface overflow rate, that is the settling velocity of the concerned size of the particle. So Vs is the surface overflow rate. Vs is the surface overflow rate. Vs is the surface overflow rate, right? So can I write down discharge Q divided by surface overflow rate is equal to the plan area. Discharge Q divided by the surface overflow rate is equal to the plan area. So this is my first expression. Discharge Q divided by surface overflow rate is equal to the plan area. Now the second expression is volume of the tank is equal to volume of the sedimentation tank volume of the sedimentation tank is equal to discharge multiplied by the detention time. Okay. Volume of the sedimentation tank is equals to discharge multiplied by the detention time. Now next, your detention time TD is equal to height of the settling zone divided by the surface overflow rate. So this is height of the settling zone divided by surface overflow rate. Second, this detention time is also equal to the length of the tank divided by the velocity of flow. Next, discharge Q is equal to surface overflow rate multiplied by the cross-sectional area. So this surface overflow rate is nothing but Vs, right? So that's why I'm writing it here. Any other formula is left? Okay. And also the volume of the tank, volume of the tank is L into B into H. Okay. So this is just one of the primary case from where you can expect a question. This year also we got one question from here. The question was, you need to calculate the plan area of the sedimentation tank. They have given you the discharge and they have given you the surface overflow rate. So simply you have to divide discharge with the surface overflow rate and that gives you the plan area. Okay. So this is how this analysis goes. So this is just one of the cases. When you read this subject in detail, you will going to see the different cases, how the different sizes of the particles are removed. Then there will be some size of the particle which may not be removed. And accordingly, we calculate the efficiency of sedimentation. Okay. So this is how it goes. Chalo, so this is what I have to tell you. You can just take the picture of this, right? You can take the screenshot of this question and you can try by yourself. Calculate the surface area required in an ideal settling tank to ensure the removal of all the discrete particles with the settling velocity of 0.0028. So settling velocity Vs, which is the surface overflow rate, settling velocity of the concerned size of the particle is given to you as 0.0028 meter per second. Okay. Then from a flow of 550 meter cube per hour, discharge is 550 meter cube per hour. You need to calculate the plan area. Now only thing that you will going to commit a mistake is in the units. Here the surface overflow rate is meter per second and here the discharge is meter cube per hour. So either you convert this R into seconds or you convert this seconds into R. So simply plan area is equal to discharge divided by the surface overflow rate. So discharge is equal to 550. I convert this into seconds. So this will be meter cube divided by 60 seconds. So this will be meter cube per second whole divided by the surface overflow rate, which is 0.0028. So accordingly, you will get an answer that will come out in meter square. Okay, you can solve this. Similarly, you have one conventional question. Again, this is a very good question. If you can try this question, you can actually know all the basic concept. This is the one question that will actually going to help you to remember all the formulas. Again, you can take the screenshot of this question and you can try by your own. Okay. Chalo, so this is what I have to offer today. We have discussed in detail about the analysis of sedimentation for the continuous flow type horizontal tank. Horizontal flow type tank, which is a category of continuous flow type tank. Okay. My dear students, again I would like to remind you, our Telegram group link is given in the description box. If you want to have the lecture PDF, if you want to enjoy the daily quizzes, if you want to get early job notification updates, you can join our Telegram group. We at IMS Gate Academy, again we offer 800 hours of live teaching in 4 different forms. First one is the online, second is offline, third one is the hybrid, and fourth one is the self-learning program. where this 800 hours of live teaching is provided with interaction along with doubt solving. Along with that, we provide you with the theory and exercise book containing 4,000 plus practice questions, well versed in level 1, level 2 and level 3. Along with that, we provide you with exclusive GATE question bank containing 34 years of GATE questions, in which we have provided the detailed solution, alternate solution, video solution, along with the key points and chapter overview. We provide you with 12 personalized one-to-one mentoring session, and IMS Gate Academy is the only institute in the country to do personal mentoring to their students. We provide you with India's largest test series containing more than 130 plus tests, which includes chapter test, subject test, multiple subject test, advanced subject test, and the full length mock test with the video solution. If you want to speak to our counselor, you can just dial these two numbers. You can either get Rahman sir or Chaitra ma'am, and even if you want to speak to the mentor, again you can ask the counselors to arrange a call. Definitely IMS Gate Academy is ready to help if you are willing to dedicate some extra time and if you are ready for the hard work. So thank you so much, my dear students, for listening patiently. I'll be back on Wednesday at same time 3 p.m. to 4 p.m. with another exciting lecture of this foundation course. Thank you so much. Have a great day ahead.